So again, the parametric equations for a line are through x1, y1, and x2, y2 are as follows. T is a parameter, and as t varies, we trace out the entire line. Now, let's consider what happens if we want to do a set of parametric equations for, say, a circle. The circular definition of the sine and cosine function tells us what we need to do. If we have a circle of radius r centered at the origin, then xy lies on the circle provided that x is r cosine theta and y is r sine theta. It's just your definition of the sine and cosine in terms of a circle. So that your parametric equations for the circle are x equals r sine theta and y equals r cosine theta. Gives us a circle of radius r about the origin. Theta is your parameter, and the point xy goes all the way around the circle every time theta goes from 0 to 2 pi. So if we let theta vary from 0 to 2 pi, these equations will trace out the complete circle. And there should be no big surprise there. Now let's think about what we would do if we wanted to get an ellipse. Okay, well, if we want an ellipse, then we want a greater effective radius, or whatever we want to call it, in this direction than in this direction. Well, why don't we just then, for example, if we want to have a distance 2 out here and a distance 1 here, let's let x equal 2 cosine theta and y equal just plain old 1 sine theta. Then when theta equals 0, of course, x equals 2, since the cosine of 0 is 1, and we're out here at the point 0, 2. When theta is equal to pi, the cosine is negative 1, and we're over here at x equals negative 1. And of course, whenever theta is 0 or pi, the sine of theta will be 0, and we will be on the x-axis. So that we see that parametric equations for at least this ellipse are y equals sine theta, x equals 2 cosine theta. Okay? And if we had different numbers here, a here and b here, it should be obvious now that y would be equal b sine theta and x would equal a cosine theta, and that would give us an ellipse with a semi-axis a here and a semi-axis b here. Again, the parameter is theta. Now this is consistent with the equation of an ellipse with semi-axis 2 in the x direction and semi-axis 1 in the y direction. That is, I've claimed that the figure we have up here does give us an ellipse. Well, if it gives us an ellipse, then because of the points on the x and y axis, a had better be 2 and b had better be 1. So we have x squared over 2 squared plus y squared over 1 squared equals 1. Is that consistent with these equations here? Turns out that it certainly is. It's true, since if y equals sine theta, then y squared over 1 squared is sine theta squared over 1 squared. And if x equals 2 cosine theta, then x squared over 2 squared would be the quantity 2 cosine theta squared over 2 squared. And since then we need to see that this sum here gives us 1, since this represents x squared over a squared plus y squared over b squared. Well, it certainly does. If we zoom in a little bit, we see that 2 cosine theta quantity squared over 2 squared, well, that's going to be 4 cosine squared over 2 squared, which is 4. 4 divided by 4 is 1, so we just end up with cosine squared of theta here. And over here, we end up with just sine squared theta, obviously. And cosine squared theta plus sine squared theta equals 1, as it must. Okay, so that this equation is completely consistent with this definition, because if we use these definitions for x and y, then x squared over 2 squared plus y squared over 1 squared does equal 1.